We're back! Anyways, I know you've been struggling with these the past couple days when you've been looking at graphs that have vertical asymptotes and limits that go to infinity. So we're going to flesh it out a little bit more with these examples. And so I have one here for you that hopefully you said, yay, I know something I'm supposed to do with it. Shout out the F word. Yes, go do that. Pause the video. Factor, duh. What were you thinking? Anyway, so I can see that's going to cancel, which of course gives me a hole in the graph, so that I'm really just graphing the stuff that's left over. So, excuse me, I've made my graph grid, and I know I have a vertical at x equals -2, so I'm going to draw that in. And then later I'll have to make sure I put a hole at x equals -1. So I'm curious, and then my horizontal asymptote, so my vertical asymptote was x equals -2, and of course I have this hole. And then my horizontal, when I look at the degree of the numerator and the degree of the denominator, I see that numerator is less, so that gives me a y equals 0. So I'll dot that in. And now I'm interested in what's happening to the left and right of that vertical, because that'll give me an indication as to basically which quadrant of the graph that I'm in. So if I do -1 to the left and -3 to the right, and of course I'm going to plug them into the reduced form, that's less math for me, so I'll have 1 and -1, and that way I know, for those of you that had me in pre-calculus, you know that these are the sheep and they can't get past the electric fences, but they want to go try and play with their little sheep friends. So that little sheep tries to get out of his fence, can't. This little sheep tries to get out of the fence, can't, and can't down here. And so there's my polynomial graph, but I have to remember that at -1, I'm supposed to have a holy sheep, Batman. So I'm going to come back, erase that, and put a hole in there. Just like that. Now, of course, one other piece about graphs that are important is it would have been helpful probably to try and find an x-intercept. And of course, that means y is 0. So I set this fraction equal to 0. Well, our fraction is never going to be 0 because there's a 1 on top. So that means there's no x-intercept. And if I look, the graph verifies that. Remember, I had a horizontal asymptote on the x-axis. And for the y-intercept, I would plug in 0 for x, so I'd have 1 over 0 plus 2, which is a half. And so, as a little sloppy here, I really should be hitting a half and finishing out that graph from the hole. So, I've put all the important pieces on my graph. You should now be able to remember how to do all of that stuff. And of course, this bottom sentence is just restating something that we've been talking about in class, is that some of the x values don't create verticals, just like in the particular function we chose above. Instead, I get a removable discontinuity, aka a hole, which you actually told me in class the other day because I asked you what types of discontinuities were removable and you said holes. So what could happen with this is if I wanted to remove that, then I would simply have to define the function for whatever the limit is. So I actually know what the limit is because once I canceled that out, I plugged that number in at -1 because it didn't make this new function illegal. So I would just go back and define f of x as a piece function, and I could use the original, well, I could do 1 over, pause for a second here, the original function x plus 1. So literally put this original function in here, and that's for everything except x equals 2, -2. So it would be for x equals 2, and okay, let's try that again. Okay, that's better. I made more room for it. So I could use the original function everywhere except -1 and -2, and I could use the simplified version when x happens to equal -1. And that would be a way to fill in that hole, and now it's actually part of the graph. See you on the next video, kids!